Last time we started talking about proofs, and we were mostly talking about best practices for proof writing. In this video, we're going to be walking through some more concrete structures that our proofs can take. Namely, we'll be talking about 4 proof techniques. We'll be talking about these first 4 today. This last one, proof by induction, we'll push off until the next class. So these are really more broad structure ideas than hard and fast rules for how we might prove something. Occasionally we'll come across proofs that use multiple of these ideas, but as far as the relatively simpler proofs go, we'll typically use one of these techniques. Our first style of proof is a direct proof, and this is probably the most common. It is what we do when we have something that we want to prove, and we start with our assumptions and then follow logical steps and come to our conclusion. So for example, if the thing that we're trying to prove is an if-then statement, then we assume that P is true, and we show that therefore Q must also be true. Another situation where this might show up, trying to show that all of something has a certain property. This is really just another way of phrasing an if-then statement. Let's look at an example. Let's say that we want to show that for all integers a, b, and c, so for any collection of integers, if a divides b and b divides c, then it must also be the case that a divides c. So if you haven't seen this notation before, this vertical line means divides, and we're talking about things like, well, 3 divides 6 because it goes evenly into 6, 7 divides 14, however, 5 does not divide 14. So we want to say that if we have some triplet of numbers, some triplet of integers, a, b, and c, so whole numbers, that if this is true and this is true, then this is true. Okay, so what does a proof of this look like? Well, to determine how to prove this, to work something like this out for ourselves, a good first step is to play around with a few examples. 3 and 6, 6 and 12, therefore 3 divides 12. Okay. But when it comes to actually writing down the proof, if we are proving it using the direct proof technique, our proof structure should follow this general format. We start off with our assumption, so we are assuming that our triplet of integers, a, b, and c, has the property in question. If P, and then we're going to show that the conclusion is true, then Q. So we state our assumption, there's going to be some logic in here, and then we conclude with the thing that we're trying to show. Because we're just doing this directly, we call this a direct proof. I also want to point out that when we phrase something like this, let a, b, and c be integers with this property, we're saying that they can literally be any integer as long as it has this property. In other words, we're considering all possible values that a, b, and c can take. We're not just listing off a few examples, we're doing the infinite collection of all integers that has this property. Okay, so what logical steps go in the middle of this statement? Well, when we say that something divides something else, so for example, 3 divides 6, what we mean is that 6 can be written as 3 times some other integer. In this case, it's 2. But for an integer like a to divide another integer like b, it has to be possible to write b as a times some new third integer. So for our proof here, we're going to be using that fact twice. Because a divides b, there's some way of writing b as a times something else. And because b divides c, we can write c as b times something else. So we're going to give these things names. We're going to call them, in this case, h and k. That was mostly an arbitrary choice. There's some convention as to which letters to use when, but that doesn't hugely matter much, especially not right now. So now that we have our b and c written out this way, we have these equations that we can work with, and we can use other logic that we already know. For example, if we have 2 equations, we can substitute b in for the second equation, and we can rewrite this as c equals kh times a. In other words, a times some other integer is equal to c, which again, now we're back to the definition of what dividing something means. We can conclude that a divides c. As it turns out, therefore was a little awkward there, but we can just change that to, we conclude a divides c as claimed, which is pointing out that, hey, this is the line that we were looking for the whole time. We have assumed our initial statement, we have assumed that p statement, and we have ended up through some logical steps resulting in the q statement. Right? So now that we're done, QED. Okay, second technique. Instead of proving something directly, we're going to instead prove the contrapositive. So remember, the contrapositive is where we transform a statement like P implies Q to the statement not Q implies not P. For example, since all squares are rectangles, an equivalent statement would be, if a shape isn't a rectangle, then it's not a square. So we've switched the order and negated both statements, and if a statement isn't a rectangle, well, we sure as heck know that it isn't also a square, because this square would be an extra property. Anyway, once we've made this switch, the procedure is basically the same. We are still assuming a component and then trying to use some logic to come to some conclusion. So, for example, if my theorem is, if n squared is even, then so is n. This is something that I can do directly. It's possible to prove this directly, but it's actually easier to, instead of proving this statement, to prove the contrapositive. So our structure is the same. We are assuming something, and then we're going to use some logic to come to a certain conclusion, which would then prove this theorem. Since we're doing something that isn't direct, it can be helpful to, up front, just point out what the general plan is. If we're doing something other than sort of the straightforward P implying Q, then it helps to give some guideposts. So, for example, here I might say, let n be an odd integer, so we are assuming Q negated, so we're assuming that n is not even, and the general game plan is to show that n squared is odd. So we're just going to say that up front. Let n be an odd integer, we'll show that n squared is odd. While this is a little bit of extra information here, I would still say that this is reasonably concise. We're not elaborating too much on things, and we're just giving a little bit of guidance as to where we're going with this. I'm picturing a bad courtroom show where the defense is trying to say that, hey, if n squared is even, then so is n, and right out of the gate they start off with, let n be an odd integer. And so naturally the prosecution's like, oh, objection, why are you talking about n being odd? We're clearly trying to talk about this other statement. Well, just like with that, we want to be clear with where we're going. We want to say, oh, no, it's cool. We're trying to prove the contrapositive. We have a plan. When you're reading through one of these, you don't want to also be trying to figure out what the proof writer is trying to do. You really want to be focused on, like, what are these logical implications and does each step make sense, rather than, like, what's this whole system. So we don't want to be cagey with our explanations of what the general plan is. This is basically our way of saying, hey, by the way, we are doing a proof by contrapositive. All right, so where are we going with this? Well, if n is an odd integer, then by definition, it is equal to some even number plus 1. A number is even if it can be written as 2 times something, so an odd integer can be written as 2k plus 1 for some integer k. So now that we have this fact, we can write out what n squared looks like. N squared is, well, this thing squared, and with some algebra, we can manipulate it to be equal to this thing on the right. And notice that this is enough to say that n squared is odd. We just want to be careful. We want to make sure that we're touching all of our bases. We want to point out that this thing in parentheses is an integer. Just because a number can be written in this form doesn't automatically mean that it is odd. It has to be the case that the thing in parentheses here is an integer. Thankfully, since k is an integer, so is 2k squared plus 2k. So this is one of those pieces that we could get away with not including. However, especially for something like this, it's best practice to include a reason for why this statement implies that n squared is odd. Since it is, we are done. QED. Next up is a proof by contradiction. So the idea is that we want to show that some statement is true. We want to show that P is true. And the way that we'll go about it is we'll say, all right, let's hypothetically assume that P isn't true. Well, since P isn't true, then we have this other statement, and then this implies this, and then through some logic we come to some absurd conclusion, like 1 equals 5. So if P isn't true, then 1 equals 5. Well, since clearly 1 doesn't equal 5, P must be true. So this is our general form. Assume that P is false, and then come to some conclusion Q that is known to be false. Therefore, the only weak link in this chain was our original assumption. Therefore, our assumption can't be true. P cannot be false, therefore it must be true. Okay, let's see an example of this. Let's say we want to show that there are no integers n and m that make this equation hold. N squared equals 4m plus 2. That there aren't any pairs. Well, you could start trying to do this, start listing out pairs of n and m, and see that each time, well, there's no way that we can make this work. However, if we actually want to prove this, we need to show that it's true for every possible choice of n and m. And one way to do this, in this case probably the easiest way of going about proving this, is by contradiction. We're going to assume that the statement is false, and then come to some absurd conclusion. General framework for a proof by contradiction is that we want to start off by assuming the negation of the thing that we want to say. So assume, and here's where it's helpful to point out, hey, by the way, the proof that we're doing is a proof by contradiction. So we're assuming the negation of the statement. So assume that there are, in fact, integers n and m where this equation holds. And then we're going to do some logic, maybe some algebra, and come to some impossible conclusion, and then conclude that our assumption was false, and that in fact there is no such pair of integers n and m. All right, how do we actually go about this? Well, the contradiction that we are angling towards has to do with showing that something is even, and that it's equal to something else that's odd, and then that of course can't happen. So here's how we get there. Since n squared equals 4m plus 2, we know that n squared must be even. And by this theorem that we had just done, so if you'll recall, we had recently proven that if n squared is even, then so is n. Well, we're going to use that now. So by the above theorem, n is also even. So this is a situation where maybe it would have been a good idea if we had numbered our theorems, but that ship has sailed. So we're just going by the above theorem. Since n is even, we know that it's possible to write n as 2 times some integer for some integer k. That's what it means to be even. Well, in that case, we know that n squared has to be 4 times this number squared. That's just, squaring both sides. And therefore, by plugging this back into the equation and dividing across by 2, we can see that, well, whatever this integer k is, it fits into our equation this way. So notice that 2 times k squared is an even number, and 2y plus 1 has to be an odd number. And if we're saying that these two numbers are equal, well, you can't have something be both even and odd. Right? So we now have a false statement. We know that this statement can't be true. Therefore, the only weak link in our system, the only other explanation, is that our assumption was false. Therefore, our theorem has to be true. QED. Sometimes if we're trying to prove some statement like P, then there may be some other component of what's happening that dictates how exactly we want to go about proving this. The example that we're about to do our approach might differ depending on if n is even or odd, even if this isn't exactly what we're talking about in the first place. This is where proof by cases comes in. We're going to take two parallel tracks and prove that P is true in both situations. So we have this mostly irrelevant property Q. Well, if Q isn't true, then we're going to directly prove P. And then if Q is true, we're going to prove P. If some number is even, then our statement is true. And separately, if that number is odd, then our statement is true. Therefore, in all cases, our statement is true. It's certainly possible to have more than two cases, but in this example, we're just sticking to two. So the theorem that we're proving here is that n cubed minus n is always even for any integer n. And we can play around with this. If we plugged in 2, we get 8 cubed minus 2, 6 is even. If we plug in 3, 27 minus 3, 24 is even, and we could keep going with this. And if you did this, you might notice that whenever we have an even number plugged in, we get an even number cubed is even, minus even is even, and odd number cubed is odd, minus odd is even. So whether or not n is even, in either case, n cubed minus n is going to be even. So we can certainly make that a little bit more rigorous, but the general structure is here. If we want to prove this, then we want to state the fact that we are doing a proof by cases. We want to be very explicit whenever we're doing this. So we're going to say we consider two cases, and then say what these cases are. It's whether or not n is even. We want to make sure that the cases that we're considering hits all of our bases. And then we can run two parallel proofs. And once we've come to the conclusion in both cases that our statement is true, in this case, the statement n cubed minus n is even, then this is going to be true for all possible n. I'll fill in the details here if you're curious, but the point of this is to illustrate the structure of what's happening here, rather than getting into the nitty-gritty of these. So if you'd like to see the details, go ahead and pause the video. When going about proofs in the future, it's certainly possible to use some combination of these ideas. But at least early on, let's keep straight which of these techniques we're using, what our general framework is. That way we can be sure that we are phrasing things in the right way. Okay. One last thing that I wanted to point out is that throughout all of the proofs that I've been writing, while this is certainly maybe sort of robotic sounding, it always reads like a paragraph. We have sentences that may be a little bit choppy, maybe not great prose, but still is phrased and structured as a paragraph. An alternative for a lot of this is using various symbols, like for all, every, implies, and using abbreviations. This is okay because these are really stand-ins for actual complete sentences. We want it to be the case that we are writing sentences even if we're using some sort of shorthand, like various notations that we've talked about. All right, that's it for this video. We will do proofs by induction next time.